So picking up where we left off on combinational loading, the last problem that we're going to do in there, let's say that we were given a situation where it had a variety of loads on it. It had a torsional load, it had an axial load, it had shear, it had a bending moment. And you can get these in a variety of places. One that comes up is maybe that you've got some sort of a signpost, and you have a rigid sign on it. Okay, and this sign obviously has some weight, and if the wind is blowing across it like this, you could end up with torsion. If you're looking down here in this region here, you could end up with torsion, you could end up with a bending moment, you could end up with an axial load. So maybe not exactly the situation, but it's fairly common to come up with things like this. So to speed this along, I just put the diagram down here that we've got so much torque, 6.75, and we're looking at this point here. So we've got 6.75 k-feet, or thousands of foot-pounds. The axial load is 50,000 pounds. Then the shear at that point is going to be minus 9.23 K, or thousands of pounds. And then the bending moment at that point would be minus 2.31 thousand pound-feet, or K-feet. And let's say that this is all applied to something of circular, solid circular cross-section, maybe some sort of a mill shaft or something like that, has a radius of 2 inches, so a 4-inch diameter round shaft. And we'd like to look at the stresses on that. We'd like to look at all of the stresses due to torque, the stresses due to bending, and things like that. So with that, let's start our work on that. We could talk about for torque, we'd have what? That the torque, the shear stress due to torque is equal to the torque times the radius divided by the polar moment of inertia. Remember that? It's a good review as we're getting close to the end of the term. And our value for torque is right there, 6.75 k-feet, thousands of pound-feet. And then I need to multiply that by the radius, which is 2 inches. If someone gives you diameter, be careful, it is the radius. So we have 2 inches. And then I'm going to need to divide by the polar moment of inertia, which is going to be pi times the radius, which would be 2 inches, taken to the 4th power, divided by 2, and that'll be inches then to the 4th. I have a units problem, so I'm going to have to multiply this by 12 inches in a foot. That should take care of my units, and when you go through this, you then end up with 6.45. We still have thousands of pounds, so I will say that this is KSI. A KSI is 1,000 PSI. So that's our shear stress due to the torque. Questions with that? Now if we look at the axial, as far as axial goes, and if we were to put this on an element, we'd probably have something that looks like this, right? That's what that torque would look like. If we were to put axial on an element, we'd have something that probably looks like that. That would be the axial. And that's pretty easy, that sigma is equal to the force divided by the area, going way back to the beginning of the term. So we have 50,000 pounds, or I'll say 50K, divided by the area, pi r squared. So we have 2 squared inches squared, which gives me 3.98 KSI. Okay, so that's the tension apparently due to the axial load. If we look at bending, bending will have 2 parts. We have the shear, which we could, we have our equation. Remember that the shear stress to bending is equal to VQ divided by IB. But remember, one of the stipulations on that equation was that it had parallel sides. Does our specimen have parallel sides? So actually we can't use that because it has to have parallel sides. But I think we can still get through this problem. I think we've lucked out on this, because if I look at this point A here, that's at the top, that's at the extreme edge, and we know it either at the top or the bottom, what's the shear going to be? Should be 0, shouldn't it? So I think even though this equation won't work, we recognize that Q is going to be equal to 0. Therefore, our shear stress due to the shear from bending would be equal to 0. Yes?
Why is the whole moment of inertia there divided by 2?
This one right here? Why wouldn't it be? That's with the diameter. If you use the diameter, it's 32. Yeah. If you're using the radius, it's different than if you're using the diameter. Uh-huh.
So Q is 0 because there's no area.
Q is equal to 0 because, yeah, there's no area above the point, or beyond the point, I should say. So the normal stress due to bending would be equal to, what do we have? Sigma is equal to minus my over I. So what does that look like? We've got 2.31. That's a negative, and that with that negative, those cancel out. So I'll have 2.31 k feet. And then the y, if I look at the neutral axes would be here. So what's the distance from the neutral axes up to point A? That'd be the radius, wouldn't it? 2 inches. And then here I'm going to have the polar moment of inertia, which would be pi times the radius, 2 squared, divided by 4. And you might say, well, why this is 2? Well, remember that for a really any section, but certainly for the circular section, we could say that the polar moment of inertia, which sometimes we use the symbol J for, is equal to the moment of inertia about the x-axis plus the moment of inertia about the y-axis. So that would be why we would expect the polar moment of inertia to be twice the size of this. Now that's going to be inches to the fourth. I still have a units problem. I'm again going to have to multiply by 12 inches in a foot. So I can take care of the units, and we come up then with 4.41 KSI. Just got it in there. Okay. So if I were to come over and put this bending onto an element, what does that look like? We'd probably have some shear due to bending that we just found was 0 in this particular case. And then we have some normal due to bending. Looks like we've got that, right? So I probably need to put these together. I need to take this, which is going to stand on its own, but this axial looks an awful lot like this sigma that we have down there. So I probably need to combine these, don't I? If I take this and I combine it with that, in adding them together, they're both positive. What do I come up with? 8.39 KSI. So I'm going to add those two together. So I'll start a new page as I do that. So I'm going to take my shear stress as 6.45. So I'll draw the element here. And we've got the shear stress, 6.45 KSI. And then my normal stress, I'm going to take 3.98 and add it to 4.41, so I get 8.39. So I've got that here at 8.39 KSI. Are there concerns? So, that's the element that we would have at A, okay? Because it represents the shear stress due to the torque. The shear stress due to bending was 0, luckily, because I couldn't deal with it otherwise. We are not prepared to deal with the shear stress in circular shafts. But the axial load, the axial tension was 3.98, and then the bending stress was a tension, 4.41, so I added those together. So I could take this one more step if I wanted to and actually put this on Moore's circle. Maybe we'd like to figure out, well, what are the maximum stresses? Now we'll recognize those maximum stresses at the principal orientation. So we'll draw more circle of stress. So I have sigma here in KSI. I have tau here in KSI. Let's see if we can do that. So if I look at the X face and the Y face, just to give us something to talk about, I have what, 8.39, so there must be 8.39. And on the X face, the shear on the X face is going to do what? Tend to rotate it clockwise, isn't it? So I'll have 6.45. So there is the X face, that is 8.39 and 6.45 KSI. And then the Y momentarily might be a little bit confusing. We don't have any normal stress, so that just means that they're going to be on the axes there. The shear stress, that tends to rotate it counterclockwise, doesn't it? So we'd be down here at minus 6.45, and there is your Y right there. So Y is 0 and minus 6.45. So I don't know that we've done one like that, so that was a good chance to do that. So there's our diameter for Moore's circle. I bring the pencil compass in here. I have to cheat on it just a little bit. There we go. Okay. So there's our circle. We could come up with the center of it. That's going to be 8.39 plus 0 divided by 2, so that gives me 4.19 KSI. The radius is then going to be, if this is what, 4.19, be the square root of 8.39 minus 4.19 squared plus 6.45 squared, which gives us 7.69 KSI. So then we could talk about sigma 1 if we wanted to right here, and sigma 2 if we wanted to right there. Sigma 1 being the principal at the center minus the radius. So we come up with, what would that be, minus 3.5 KSI. And sigma 2 being the center plus the radius, which would be 11.88 KSI. And then we should probably handle this point up here. What's that going to be there? Tau max. So tau max, the in-plane shear stress. I haven't talked about the absolute maximum because I don't know what's going on with Z, but if I talk about the maximum in-plane, that's just going to be equal to the radius. So I have 7.69 KSI. So you've got some homework problems on this. They can be fairly involved. That's good from the sense that it gives you a lot of review of what we've done over the term. Then we put these stresses together, and we can even take it further onto Moore's circle and then start to talk about what are the maximum possible stresses there if we start to look at different orientations.
So the new stress is a little bit different.
The new stresses we're doing what with?
The sigma 1.
Mm-hmm. These would be principal. So if we're rotating this down to a principal orientation, it would be right there. Which means that if I were to draw this on an element, I haven't done that, but the element would be rotated like that. And it would rotate through this angle here. If this is theta, this is what? Theta over 2? Yes?
So we put the normal stresses. Why would they not be in the Z direction?
Normal, the In the z, oh, you think the z direction is coming out of the page?
Yeah.
I guess I probably wasn't as clear as I should have been on this. If we were to take a view of this point here, we're looking essentially at the top of that shaft, if you will, and there is point A right there, and we drew our element actually like that. Okay. And I don't know that x and y is necessarily that important. I just labeled it here to give us something to talk about. You could take whatever directions that you wanted. Other questions? Good. So tackle those homework problems because they're fairly involved and they're good for a lot of different reasons. Help you with review and whatnot. Well, let me move on to the next section and where we're going to spend the most of the rest of the term, which is in beam deflection. So with beam deflection, I'm going to do this derivation with a cantilever beam. You could use a simply supported beam, but I'm going to take a beam that we've applied some load to. I'm going to draw a fairly thin beam to make it a little easier to envision here. We'll apply a load to that. Anyone that's maybe in their boredom put a ruler on the edge of the desk and has been putting a load on it and making it vibrate and playing a little tune on it or something recognizes you can do something like this. And maybe I should look at the direction here. I'm going to take this as the x direction so you can see that it's definitely deflected down from that. And I'm going to talk about this deflection in here. That tiny little deflection there, I'm going to talk about lowercase v. So uppercase v, that's the shear in the bending, the shear and moment diagrams. We've talked about that a lot. Lowercase v, we typically talk about beam deflection. And then if I come along here some distance that I will call dx, I'll have, you could imagine, more deflection. And so I'll call that v plus dv. Okay, and you can see that you've got some deflection there. You have more deflection there. You'd imagine you probably have your maximum deflection out there. Well, I'm going to look at the radius of curvature of the beam at this point. Okay, so that's the radius of the curvature rho. And we talked a little bit about that when we went through the derivation of the stresses due to bending. We said even the beams in this floor, as we came in here, me included, not trying to pick on anybody, but the floor deflects a little bit under our weight, right? And so there's a radius of curvature. In that case, it'd be way up in the air here. Fairly hard to measure because it's going to be quite a large distance unless we have a tremendous deflection. But we do have that. And I'm going to say that this angle in here is d theta. And then this gives me an arc length here that I'm going to say is ds. Okay. And I'm going to say that this angle in here is theta, the angle of rotation there. So maybe I should spell a couple of these out. We're going to say that v is defined as the deflection. And we're going to talk about theta as the slope of the beam.
Wouldn't that slope be changing further back you go in them? Because obviously
Sure.
slanted.
Yeah. It would be 0 back here.
Yeah.
Yeah.
At the very end, it'd be a straight.
Yeah. Both theta and v will be a function of x. It's going to change as you go along for sure. Okay, so let's make some observations here. If I want to talk about ds, that arc length, I could say that that's equal to rho times d theta, right? If d theta is in radians, I multiply that by rho, that gives me the arc length there. So solving for rho, I could say that rho, because oftentimes rho is hard to find, so I want to solve for it, rho is equal to ds divided by d theta. And maybe I will invert rho, so 1 over rho is equal to d theta ds. And I'm going to say that that's pretty close to d theta dx. So ds is our arc length there. That's that distance there, whereas dx is the horizontal distance. And if our deflection is small, like we think about the deflection of the floor beams here, or the deflection in the roof might be a little bit larger, this difference between the horizontal distance and this arc length is going to be very, very small indeed. So we'll say that this is approximately equal to each other. That should make our life a little easier. Let me then talk about the tangent of theta at this particular point. So I could talk about the tangent of theta being equal to, remember the definition of theta is opposite over adjacent, so I could just say that this was v plus delta v minus v. So that's essentially looking at this little triangle right in there. And I'm going to then divide that, so that's the opposite over the adjacent. The adjacent is dx, right? And if I go through that, I could say that that is dv over dx. And for small angles of theta, I could say that theta is equal to dv dx. So I can get rid of the tangent. If you have a small enough angle, the tangent of the angle is just equal to the angle. And when we start to think about how large this angle is in a situation like the building we're sitting in, the angle is pretty small. So we've got a pretty good approximation here with this one and with that one. So now I can put them together. If I've got that 1 over rho is equal to d theta dx, I could say that that's really equal to the derivative with respect to x of dv dx, right? Because isn't that what theta is? Yeah. Which gives me what? The second derivative? Second derivative of v with respect to x. Well, we'll have to go back and remember one more thing. So I'll put that here. So from our derivation of beams and bending where sigma is equal to minus my over I, when we derived that, we had the following equation, that 1 over rho was equal to minus m over ei. And I did some substitution in there because we didn't want to have to deal with rho, but that's an important equation because I'm going to use it again. So I could say then that 1 over rho, that's this thing, isn't it? So I can say that minus m over ei, and that's just what that is, the moment, over Young's modulus, over the area moment of inertia, is equal to the second derivative of the deflection with respect to x. Or sometimes we'll write this, that minus m is equal to, multiplying both sides by ei, is Young's modulus times the area moment of inertia times v double prime. This is, of course, v double prime. Okay. Now, if you go through your author and your textbook doesn't have that negative sign there. I take deflection positive down because most of our beams deflect down. Your author takes it as positive up. Just a little bit of a difference there. Okay. But whether you have that negative sign or not, the equation still holds, and the process we'll go through is very similar. So if I want to talk about the deflection, what I'm going to have to do is I'm going to have to come up with an expression for the moment. I'm going to have to then integrate it twice. As I integrate it twice, I'm going to have two constants of integration and have two boundary conditions to solve for those constants of integration. So this is my deflection equation. Well, let's see if we can go through an example and maybe make it slightly less mysterious. Questions before we do that? Let's try that. So we'll go back to a very common example, a simply supported beam with constant distributed load. Pretty easy to do with this. So simply supported beam. So, whoops, I did Q, which is equal to W. Probably a good thing I made that mistake so we can talk about that. When I learned this, we always use distributed loads as Q. Timoshenko likes to use distributed, or he's dead. He'd like to use distributed load as Q. Your author likes to use W. Probably a little more common nowadays to use W. So if you go back through the homework and what are they talking about this distributed load Q, that's just the distributed load. Same thing as W. I'll try and remember to use W as I go through lecture. Okay, so that's the distributed load. How many pounds per foot we would have there on this thing. And we'll take the length of L. So I need to come up with a moment. So I'm going to go through this thing and section it, just like we did way back at the beginning of the term before we started using the shortcut so much. So as I section this, I'm going to use my deformation sign convention. That's the shear, capital V, not the deflection, capital V. And then I've got this moment here, M, that's what I'm really looking for. And then I've got this distributed load. It's like this, and I'll go ahead and use W for that distributed load. And I'd have, of course, the reaction back here that's going to be what? W times L divided by 2. Okay, the total load is W times L. Half of it's supported here and half of it's supported there because it's symmetric, so I have WL over 2. And you could go through a free body diagram and analyze if you want to. We've done that many times. I won't belabor that. So if we look at that distance where we're going to cut through at X, maybe that's right there, maybe that's right there. It could be any place in there. And that's why this is a good example. If we started looking at having multiple concentrated loads, we'd have to section this in many places to come up with the deflection equation. But this is nice. I can just do one section on it. So as I look at summing the moment about the cut point, this cut point right here, setting that equal to 0, and I've only separated the shear for clarity. That shear actually intersects the cut point, so I don't need to worry about that shear, which is good because I don't really care about it. So I could say that I have M plus, then you're going to have some load out of this thing. That's going to be what? W times X times the distance that it acts through is what? X over 2. Okay. And then I'm going to have to subtract off what? W times L over 2 times the distance that acts through, which is X, right? So I could say that my moment then is equal to W times Lx over 2. W times Lx over 2 minus Wx squared over 2. And sometimes you'll see this written as W over 2 times Lx minus x squared. And you could actually factor out an x, but sometimes I don't because I want to make sure we recognize that as a second order equation. Okay, so, and this probably for our purposes, this is as good a stopping point for that as any, because I'm going to have to try and integrate the thing. So now if I want the deflection of this, and I think we recognize the deflection would probably look something like this. If I were to draw the deflected beam, I think you can imagine it would look something like that, wouldn't it? Okay. And if you're trying to paint, if you've got a bookshelf that's way overloaded, it might be that obvious, right? Okay. Or the beams under this floor in here, they've actually deflected like that. It's just not that obvious. It's much more subtle, and I've exaggerated this. But this is what we're looking at. So sometimes it's a good idea to have an idea of what we're going for. So we go back to the equation that we derived, where we have minus m is equal to EI v double prime. So let's use that. If I take this moment and I put a negative sign in front of the terms, I now have minus W Lx over 2 plus Wx squared over 2. So I've put that minus sign through, is equal to EI v double prime, right? Okay. Well, let's see. I'll integrate this thing. I mean, this should be right up your alley, too. This is Math 256, isn't it? Integrate, come up with boundary conditions. Is that true? Okay, great. Okay, so when I integrate, what do I come up with? Minus WL over 2 times x squared over 2 plus WX cubed over 6. Is that right? Yeah, is equal to E. I forgot something, didn't I? So, plus C, yeah, I'm going to call it C naught. I have a constant of integration, don't I? So I better put that in there. So C naught is equal to E I V prime. What's V prime? That's actually theta, isn't it? I mean, if we go back to here, theta is dV dx. So theta is equal to V prime, isn't it? Okay. So this is actually the slope. Okay, so that's going to be important when we start trying to think about boundary conditions. If someone asks us questions about the slope of the beam, it's going to be important to recognize that V prime is theta, which is the slope. Well, having recognized that, I'm looking for the deflection, so let me integrate again. So doing this again, I have minus WL, let's see, this will be x cubed, and I'll end up with, what, 12 in the denominator, right? 2 times 2 is 4 times the 3 is 12. Plus Wx to the 4th divided by 24 plus C naught x plus C1 is equal to EIV, where this is now the deflection. Okay, so I found the deflection, kind of. As you probably found out in Math 256, all the work is in finding the boundary conditions, right? I mean, if this is a partial credit test, we write this as the final answer, we probably don't even have half the problem done, do we? A lot of the work is in finding the boundary conditions. So let's look at our boundary conditions. What boundary conditions can we use? Got any ideas? Okay, great. At the deflection, V at x equals 0 is equal to 0. So he said that over here, there's 0 deflection. Absolutely true. There's probably maximum deflection in the middle on this one, although I don't know what that is. That's probably not a very good boundary condition. But as I continue looking across this, what is a good boundary condition? At x equals L, what do we have? 0. Okay, so those are a couple good boundary conditions. I actually have one more. I would know that the slope in the middle is equal to 0, right? So we could say that theta at x equals L over 2 is equal to 0. So that might be helpful, which is kind of nice to have more boundary conditions than I need, because we get into a problem, a difficult problem, if I don't have enough boundary conditions to solve for those constants of integration. But I think these are probably the most obvious. I'm going to go ahead and use those. So I put in the first boundary condition. I like this one because at x equals 0, we have 0 deflection, so I have 0 plus 0 plus 0 plus C1 is equal to 0, right? So we recognize that C1 is equal to 0. And then the next boundary condition at x equals L, now that's a little more work, isn't it? So I'm going to have minus W, when I put L in for x, I've got L cubed, another L, so I'll have L to the 4th divided by 12 plus WL to the 4th over 24. And this is something always to look at. If your loading is by a single load, a single distributed load in this case, our orders should always be the same. If we have an additional concentrated load, then we're going to have other terms that have other orders that deal with that. But since all of our loading was due to this load W, everything that has a W in it should have the same order. 4th order there, 4th order there. In fact, here I have L times x cubed, so I had a 4th order term. Here I had x to the 4th, I had a 4th order term. And in fact, as we get these constants of integration, they should have the same order, unless, of course, there's 0. So we've got WL to the 4th over 24 plus C naught times x. C naught times x, what was x? X is equal to L, so C naught times L is equal to 0. So we can solve for C naught. That's going to be equal to WL cubed over 12, because that moves to the other side, minus WL cubed over 24. So this would be 2 24ths, wouldn't it? So if 2 24ths minus a 24th gives me 1 24th. So WL cubed over 24. Okay, and you might say, well, what happened to your order? You have L cubed, but remember C naught is going to be multiplied by x. So the total order of that term, by the time I multiply this L cubed by x, I have a 4th order term. So I can be confident, hopefully, or not completely confident, but have more confidence in my substitutions in algebra. So this is C naught. Okay, so we're ready to put these in. And so we're going to plug these into that equation right there. So we can say that we have minus WLX cubed over 12 plus WX to the 4th over 24 plus C naught, which is WL cubed over 24 times x, plus C1, which is 0, so I don't have to worry about that, is equal to EI times the deflection V. So with that, I'm going to solve for the deflection V. Let's see, what are we going to have here? V is equal to 1 over EI times, let's see, if I change this to get me a 24 in there, I could say that this, if this is 24, I have 2 in there, right? So I'll bring out a 24. And what am I going to have left? Minus 2 WL x cubed plus WX to the 4th plus WL cubed. I forgot an x, didn't I? So WL cubed x, WX to the 4th.
Now this derivation is only good, this equation is only good for simply supported with single distributed load.
Right, yeah, and I don't, yeah. I'm not sure that this is, we'd want to even call this a derivation. This is actually just going through the problem for this particular scenario. Yeah. So if someone changes the load, if they add a concentrated load here, we'd have to go back through that. But we'll talk about that. So let's see. Are my orders still the same? 4th order, 4th order, 4th order. That's good. I think I can tidy this up some more. That the deflection is equal to, what are we going to have here? I can pull a W and then X out, right? So WX divided by 24E I times minus 2 Lx squared. Is that right? Minus 2L, yep, plus x cubed plus L cubed. So what if I look at the units on this? So what units would we have in the parenthesis? This is going to be length times length squared, length cubed, length cubed. So let's say that this is inches cubed. You have to be careful if we're talking feet, but I'll put that in inches cubed. This W is going to be pounds per foot. Yeah, we'll probably have a units problem there, won't we? So maybe I should say it's pounds per inch. So I'm going to say pounds per inch. Keep our units really nice. We'll talk about the implications of that. I'm going to say that x is in inches. And then we've got 24. That doesn't have units, but E is pounds per inch squared. That's pretty easy. I is inches to the fourth. That's pretty straightforward. So I get to cancel this and this. I've got then inches to the sixth in the denominator, and I've got inches to the what? No, I don't have inches to the sixth in the denominator. I've got inches to the fourth in the denominator. This comes up in the numerator. Yeah. Yeah, so I've got that cancels with, oh, these are in the denominator, aren't they? So I get to cancel that. One of them's in the denominator. I'm making a mess of this. So I've got inches squared, and then inches. That goes in the denominator. That goes in the numerator. This is in the numerator. That's in the denominator. This is in the numerator. There we go. Inches. Okay, so that's good. That's what we would expect our deflection to be in. Once we made it, inches. We measure the deflection of the floor in inches, probably small fractions of an inch, hopefully. Now some things came up. As I said that we probably would be tempted to put that in feet. Okay, so if that were feet, we'd have to multiply by a factor of 12. This x, that might be in feet, so we'd be multiplying by a factor of 12. And this W might be in pounds per foot rather than pounds per inches. Probably pounds per foot is much more common. So with all of those, oftentimes you're multiplying this by 12 cubed. So be real careful with your units. Okay. So it's probably worth, as you go through this problem, writing out your units and keeping a careful accounting of the units. Well, let's see if we got the problem right. If you go to your textbook and check this out, there's a table in the back. It's not the answers to the homework problems. But if you look at this here, we are in Appendix C, and I realize it's probably a little weak for you to see, but you can check this out when you grab your book. I'm not even going to give the page number because you have different copies, but if you look at a simply supported beam with a constant distributed load, we're that one right there, aren't we? And we're going to say that the deflection is minus Wx. So how are we doing? Minus Wx. So they have a negative sign in there, don't they? Minus Wx over 24EI, and then they have the minus 2Lx squared plus x cubed plus L cubed. Okay? So with the exception of this leading negative sign, and I knew we were going to differ by that, we have the same value. So those of you that were saying that this problem, going through it, we're only solving for this, well, fortunately, someone has done a lot of these for us and summarized these in the table. So if we have simply supported beams, We may not have to go through this process. If we have cantilevered beams, we may not have to go through this process. And there are handbooks out there with a lot more comprehensive cases than this. But sometimes the cases are not presented, and you have to go back through this. If you have something that you can't find a case on, you're going to go back through this process. So we'll talk about that. We'll also talk about how we can use superposition to help us with this. But for now, I wanted to get you started by going through the derivation, coming up with this equation, which works out nice from a math standpoint. You're doing things like this or have done things like this in Math 256. So you go through and you integrate that twice, and you then have to deal with your boundary conditions, and you come up with the expression. Now, if for some reason they wanted the expression on the slope, we would just come back to this, right? And we'd use C naught. We've got C naught. We'd put it in there, and we've got the deflection. So if you're interested in deflection, you can get that too, but I won't go through that. So that's the process of coming up with the deflection. What if we wanted the deflection at the middle? Yeah, x is going to be equal to L over 2, isn't it? Just go through that. And what if you wanted to know where the maximum deflection was? You could differentiate this thing, right? But before we break out the calculus, we already have it differentiated. What's that called? It's called the slope, isn't it? And we'll find that the maximum is where the slope is equal to 0. So it shouldn't surprise us that in that particular case, the maximum is in the middle also. Any questions with that? Well, I wanted to go through that and get that started. When we get together in lecture next time, we will continue on beam deflections. We've got quite a bit of work to do with this, so that's where we'll go.